Hi everyone, thanks for watching. In this video, we'll go over several examples of ionic naming and formula writing. At this point, the substances may or may not contain transition metals and polyatomic ions. I'll go over 2 examples in detail and then provide some more at the end of the video for you to try on your own. Let's try to write a name for NiNO3 The same naming rules apply just as they always have, with only one small addition. If you see a polyatomic ion, just look up its name and include it at the end. Since NO3 is definitely a polyatomic ion, I need to go to a reference sheet, find it up here at the top, and just look up to see whatever it's called, in this case, nitrate. So the first thing I write down is nickel for the Ni and nitrate for the NO3. Unfortunately, I can't totally be done with this name because nickel is a transition metal, which means I also need a Roman numeral. So let's go to the scale to figure out what charge nickel has. First, I fill in my ion quantities, 1 nickel, 2 nitrates. Remember, you don't have to guess at these numbers. The formula is there, given to you doing all the hard work and telling you 1 nickel, 2 NO3s. Now, I can't just look up nickel's charge. That's the whole point of being a transition metal. It could technically be anything, but nitrate's charge I can look up. As long as you've got the reference sheet, you can see that NO3 is -1. I've already got that labeled in. Since there's 2 nitrates, they total up to -2, and because charge is balanced, the nickel has to be +2. Now that I know nickel is a +2, I know to use the Roman numeral 2, making the final name nickel 2 nitrate. Now let's try to write a formula for gallium chloride. First thing we want to do is write the symbols for each ion, but with one problem. I see an ITE ending. That means I've got a polyatomic ion. So before I can write that symbol, I probably have to go to a reference sheet and look it up. Chloride is ClO2. So I write Ga for gallium and ClO2 for the chloride. Next, we look up the charges of each ion. Gallium is in aluminum's column, making it a +3. Chloride I can't find on the periodic table because it's actually made of several different atoms together. But again, that's why we need our reference sheet to look up. ClO2 has a -1 charge. Let's fill those out. +3, -1. And finally, we go to the scale to see if my charges balance. Clearly, with a +3 and a -1, these charges do not balance out. But if I had a second chloride, that's closer. I've got a -2. A third chloride gets me up to a -3 to balance out the +3. Now my charges cancel. Since I know I need 1 gallium, I use a subscript 1, and 3 chlorides, I use a subscript 3. Let's clean this up a little bit and get rid of everything we don't need, ending up with GaClO2 3. Now you should notice something strange here. With the subscript of 3 right next to the subscript of 2, it kind of looks like there's 23 oxygens, which is definitely not what we want. There's 3 separate ClO2s. The proper way to include these subscripts when there's multiple polyatomic ions is to include a parenthesis surrounding the polyatomic ion formula, ensuring that we know there's 3 ClO2s and not 23 oxygens. So make sure to include parentheses whenever you need multiple polyatomic ions. This makes my final formula Ga parenthesis ClO2 3. Now it's your turn to practice. Remember to pause the video and try them on your own before watching my answers. Create your own miniature scale models to make sure the charges balance, and Google image search a polyatomic ion chart if you need. So with that in mind, go ahead and pause the video and try these 4 examples. And here's the answers. For calcium nitrate, I need 2 nitrates to balance out the charge of the calcium +2, making the formula CaNO3 parenthesis 2. And in copper 2 phosphate, I need 3 coppers and 2 phosphates to get a +6 and -6 balancing charge, making the final formula Cu3PO4 parenthesis 2. The name for Mg3P2 is just magnesium phosphide. I don't need a Roman numeral, it's not a transition metal, and phosphide gets the traditional "ide" ending because it's not a polyatomic ion. For Fe2CO33, there's 2 irons and 3 carbonates, making the charges balance at -6 and +6. Since there's 2 irons, each individual ion has to be a +3, making the final name iron 3 carbonate.